Welcome back to Summarize Science. Imagine you're a robot exploring another planet, like Mars. There's no GPS to tell you where you are, and a lot of the landscape looks the same, just rocks, craters, and sand. How do you build a reliable map and not get lost? This is one of the biggest challenges in robotics, and this paper presents a fascinating new solution. The key is something called loop closure, which is basically the robot's ability to realize, hey, I've been to this exact spot before. Recognizing a familiar place allows the robot to correct any small errors that have built up in its map over time. But it's incredibly difficult when the scenery is repetitive or lacks distinct features. Cameras can get confused by similar-looking textures, while laser scanners, or LiDAR, can struggle with sparse terrain. The researchers developed a system called MPRF, which stands for multi-modal place recognition with foundation models. Let's break that down. Multimodal means it uses two types of sensors, a camera for visual information and LiDAR for 3D geometric information. And foundation models means it uses incredibly powerful, pre-trained AIs, like DNOV2 for images, that have learned to understand the world from enormous amounts of data. The system works in two main stages. First, the visual AI quickly scans through all the places it's been to find a handful of potential matches. Then, for those few candidates, it combines the visual data with the 3D laser scan data to perform a geometric verification. This second step is crucial because it doesn't just say, this looks familiar, it calculates the robot's precise 6DoF pose, its exact position and orientation. The results from testing in planetary-like environments are impressive. The new MPRF system, specifically the MPRF-BF version, achieved the highest precision in recognizing places compared to many other state-of-the-art methods. Interestingly, they found that methods using only LiDAR data performed very poorly for the initial search, as the sparse geometric data wasn't distinctive enough. But while vision was best for finding a match, the LiDAR's geometric data was absolutely critical for the second step of accurately calculating the robot's position. As you can see in these images, using only visual features or only 3D features results in many incorrect matches. However, when the two are fused together, the system produces clean, accurate, and reliable correspondences. This shows that the two senses perfectly complement each other's weaknesses. So, let's recap the important points. First, for navigating tough, unstructured environments, combining vision and 3D geometry is far more robust than relying on just one. Second, using massive, pre-trained foundation models allows the AI to generalize to new environments without needing tons of specific training data. And finally, this system goes beyond simple place recognition to provide the explicit pose estimates that are required for a robot to actually correct its map and navigate reliably. This work bridges the gap between simply recognizing a place and truly understanding the robot's position within it. It's a major step towards creating more autonomous and dependable robots that can explore the most challenging and remote locations, both here on Earth and on other worlds.